Hello out there on this beautiful day. So what we're going to look at today is revision on probability, okay? And most we'll be doing is solving problems, okay? So what I would like you to do while out there is to try and do some of the problem with us, okay? Try and really persist, okay? So we'll start with the first question. Let's look at what the question looked like, okay? And I'll encourage you at home there to what? Read the question, okay? Let's see what do you need to solve some of the problems we're going to do with us, okay? So before we do that, who uses probability as part of their job? Have you ever thought about that? Do we really have people that use probability? Yes, quite a lot, okay. And data analysts, which is a new career which is growing, they use data. Insurance company do use data. I think each and every career, especially in the future, one will require the use of data to do some statistics or probability, okay. So many career will use data, but we have lots and lots of career that use data, because if you do have data, you can calculate some kind of probability, okay. So let's look at what we have on some of the keywords. What is a sample space? A sample space, if I have a die, okay, my sample space will be 1, 2, 3, 4, 5, 6. Okay, if a die has 1 to 6, if I have a fair coin, my sample space will be head or tail, because if I flip a coin, I'll get head or tail. Then what about independent event? Are we together? Are we together? Independent event, if the likelihood of event A, if I have two events, A and B, the likelihood of A happens is not affected by the B happening. Are we together? If I flip a coin, me getting tail doesn't mean it will affect head for the next flip. Not really. Not. Okay. Dependent event really depends on the other. Independent and dependent events. So that is independent. You can see from the word independent. It's not, it's independent, and dependent can be affected by the other. Okay. So independent event and dependent event, I mean, you can think about from being independent and from being dependent. And let's look at some more keywords. Complementary event, and we're going to look at mutually exclusive event. And we'll really define this later, because we're going to look at the summary. Complementary, I'll think of this as complementary. If the probability that it will rain today is 30%, what is a complementary of that? It will be 70%, because the two add up to 1. That will be the complementary. So the probability it will rain is 30%, and the complementary of that will be not raining. Are we all together? That's the complementary of that. And mutually exclusive, they can't happen at the same time. Those are the mutually exclusive event, and we'll look at that when we look at our summary. Clearly, what does mutually exclusive look like? Okay. And this is mutually inclusive, which happens mutually exclusive. They don't happen at the same time. Inclusive can happen same time. Okay. So let's look at this, our summary. If you have two events, inclusive A and B, then we know that this is an inclusive. The probability of A or B is the same as probability of A plus the probability of B minus the probability of A and B. And this is the same as that. Okay. So inclusive, okay, meaning there's some intersection between the two circles. So you have event A and event B. Inclusive, there's some intersection between the two events. Okay. So the probability of A plus the probability of B minus the intersection, which is this part. But for mutually exclusive, so mutually exclusive event. So mutually exclusive means the two events can happen at the same time. So you have a circle there, event there, and the intersection between the two events is actually 0. There's nothing common between the two events. Are we all together? So how will this change? It will actually make this part 0. Are we together? It will make the probability of A and B occurring will be 0. Okay? So it means the probability of A or B is the same as probability of A plus the probability of B. Are we together? This is the same means as the intersection. And this is the same as OR. Are we together? But we'll definitely use the OR like that. Okay? This is another notation. Fantastic. So we spoke about complementary when we started as our keywords. So complementary events are two mutually exclusive events that together contain all the outcomes in the sample space. Are we together? For two complementary events, so we say, this is the probability not A. If I put something like that there, that means not A. And the probability of not A is 1 minus the probability of A. The same example as rain and not raining. Okay? 1 would be like the 100% minus the 30%. If the probability it will rain is 30%, what is the probability it won't rain? 100% minus 30, which is 70%. Okay. Are we together? So now, which is the same as this, probability of A is also 1 minus the probability of not A. Are we all together? Now let's talk about statistical independent. So to test where the two events A and B are independent, we have to check whether the probability of A and B is the same as the probability of A multiplied by the probability of B. So if you take the probability of A times the probability of B, and we find it's the same as the intersection, it implies the two events are statistically independent. Okay, hope this makes sense. So let's look at an example. So this is what is given. The probability of not A and not B is 0.1. The probability of A is 0.5. The probability of B is 0.75. The question is, find the probability of A and B. So firstly, what does this mean? The probability of A and not B is the unshaded region in the Venn diagram, because if event A and event B is the outside, that's meaning, which is 0.1. Are we all together? Makes sense? Okay. Now, we know that we can do this and say now, probability of A or B, are we all together? It's 1 minus what? 0.1. Are we together? Because the sample space, everything in the sample space adds up to 1. Are we together? If outside is 0.1, then inside is what? It's 0.9. Okay. Then what we can do, we can use this formula. This formula will be given to you, that the probability of A or B is the same as probability of A, probability of B, minus the intersection. Are we all together? Then what we can do, we can put everything together. We know that the probability of B is, A or B is 0.9. Are we together? The probability of A is given there, which is 0.45. The probability of B, 0.75. And we have calculated, and what are we looking for? That's what are we looking for? The probability of A and B, which is the intersection there. So let's put everything together. So this is 0.9. Are we together? and we put our 0.45 there, 0.75, and what we're calculating, which is the intersection, and we just solve this equation, okay? So what do it mean? I have to bring everything the other side, okay, because we're solving that, and if you solve this, I've added this 2, I get 0.12, 0.2, and if we solve further, we get that probability of A and B is 0.3. Are we together? So what was important with this question was we knew that this is 0.1 outside. Then we knew that this whole thing will be 0.9. That was the key part, because we know that this whole thing will add up to 1. That was the key part. And knowing that this is 0.9, then what we could do is to use the formula, which is given to us to calculate the intersection. Are we all together? And we're given 2 more information. Great. Fantastic. Okay, so we'll come back and we'll try some of the problems after the break, and hope you're ready there with your pen and paper. Welcome back again. We're still on revision on probability. So we need to look at another question and read the question clearly and see what is given there before you attempt the question. Okay, let's see what we have. So what are we given? We're given A and B are independent events. Very important. There's a word independent. What does independent mean? Okay, independent event. And we're also given that the probability of A occurring is 0.7, and the probability of B is 0.4. Are we all together? So what does independent mean? So what we know is that if event A and B are independent, so the probability of A and B occurring is the probability of A multiplied by the probability of B. And if you look at this question, we're given the probability of A and the probability of B. Are we all together? So that's what we can do. So it's actually, it will be, so as A and B are independent, so what we can do is actually say the probability of A and the probability of B is the probability of A times the probability of B. And we can multiply the 2, and we get that the probability is 0.7 multiplied by 0.4, which is 0.28. That was not really bad. But you cannot assume independent unless it's given, or maybe they ask you to prove whether it's independent. Are we all together? Fantastic. Now, the second question is, what is the probability of not A and B? What does not A and B mean? Okay, let's draw a Venn diagram and see. Not A and B is that. So this is a sample space, our sample space. Around is our Venn diagram, and this is event A. The circle is event A. Are we all together? And this is event B. So not A and B, okay, is the shaded region in the Venn diagram. We can see this is the shaded region there. We've shaded it. So we just have to calculate that. So how can we do this? So we know that not A and B, this part, it will be that intersection minus B. Are we all together? For us to calculate this piece, will be this whole B, which is that, are we together? Minus the intersection to give us this shaded region. So you don't have to write this formula. So the probability of A, not A and B, is the probability of B minus the intersection, because we have to minus this intersection to only get B only, which is the same thing. Okay, are we together? So let's put everything together now. So if we do that, we get the probability of B, which is 0.4, minus the intersection which you've calculated from A, and this will give us 0.12, which is 12%. And we know that the probability of an event is less than 1. If more than 1, just check your calculation. You might have a calculator or error somewhere there. Should be less than 1. Okay. So draw the Venn diagram to help you, okay, but not really necessary, but with the Venn diagram, this becomes better for us. Now, let's look at another question. So, but this question is a bit different. I don't think it requires a Venn diagram, but very important to read and see what is required there. So this question 3, a bag contains 6 green counters. So we have 6 green in a bag and 4 blue, okay? So what do we have total in that bag? So we have 10 counters because 6 are green and 4 are blue. So what are we going to do? A counter is chosen at random from the bag, then replaced. Very important. So you have a bag with 10 objects inside, okay? 6 are green and 4 are blues. You select one at random, you look at it and say, oh, green or blue, then you return it back. That is what is happening, because this is, you replace it back. Are we together? This is repeated more than 2 times. Are we together? Now the question is, find the probability that 3 counters are chosen at randoms are green. What is the question asking? What is the chance of, we put this 6 green and this 4 blue. What is the chance of getting green? I put my hand, I get green, I replace it. Then I do the same thing again and get green, replace it, and I do it for a 3rd time. What is the chance of getting green, green? Are we all together? And the second question is, not all same color. Are we together? So this question, the best way, I think, to solve this is draw your tree diagram. Okay. How do we draw a tree diagram? Let's see how we can draw a tree diagram. So what we're going to do is, because a bag contains 6 green and 4 blue, so we have 10 in a bag. What is the chance of getting green? Green is 6 out of 10. And 6 out of 10 is 0.6. What is the chance of getting a blue counter? Blue is, because with 4 blue is 4 out of 10, and 4 out of 10 will give us 0.4. That's the first part. Getting green initially is 0.6, 6 out of 10. Getting blue is what? 4 out of 10, which is 0.4. You can write this as a decimal like that, or you can leave it as a fraction. Then what if we do the same thing? Let's see, we do the same thing again, meaning, because we're replacing it, the chance of getting green again was still 0.6, of getting blue will still be 0.4. If we get blue and we return it back, chance of getting green is still 0.6. Of getting blue is still 0.6. Are we together? Now, we do the same thing again. What will happen? Of getting green, it will stay 0.6. Of getting blue, still 0.4, and similarly. Now, the probability of getting green, green, green will be 0.6 times 0.6 times 0.6, because getting green is 0.6, and getting another green and getting another green will be 0.6, 0.6. Okay, which is what? You can see it there, which is green, 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 which will give us 0.216. Fantastic. Okay. And the second question was find the probability that 3 counters chosen are not the same color. What does that mean? To find the probability that there will be at least one of each color. So we can do this. So what we must do, we'll say 1, which is the whole sample space, minus the probability of green, 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 minus the probability of blue, blue, blue. Are we together? So because we want the probability that 3 counters chosen are not all the same color. So we say 1 minus the probability that of same color. And same color could be green, 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 blue, 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 blue. Are we together? So we know the probability of green, 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 which is 0.6 times 0.6 times 0.6. The probability of blue, blue, blue will be 0.4 times 0.4 times 0.4. So that's the probability of blue, blue, blue. Okay, there. Now, therefore, what we can do, therefore we say 1 minus the probability of green, 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 minus the probability of blue, 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 which gives us 0.72. Okay, fantastic. I hope this makes sense, okay, and you understand this, okay. It's just 1 minus blue, 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 minus green, green, green. Okay. Okay, now let's take a break and we'll see you after the break shortly. Welcome back again, guys. We're still focusing on revision on probability. And remember to try at home. You know, you try to do your mathematics with pen and paper. Observing only and not trying the problems might not be that helpful. But when you try to engage maths by trying the problem, that's actually the best way. Okay. So let's look at what we have our next question. Okay. So our next question, which is question 4. So a password consists of 5 different letters of the English alphabet. Okay, each letter may be used only once. Okay, so how many passwords can be formed? Okay, if what? If all letters of the alphabet can be used. Are we together? So how many, so we ask ourselves, how many alphabets do we have? So we have 26 alphabets from A to Z. So we want to create a password. What is the length of a password? Using 5 letters. Okay? So how many passwords can we get from that? So this is a counting principle. So we have to apply the fundamental principle of counting. So for a password of length 5, so for the first position, how many letters can we choose? How many letters do we have? We have 26. Okay? So, but do we have to repeat them? So it's very important that each letter may be used only once. So if the first letter I've used A, I cannot use A again. So this is a counting without repetition, because I cannot use the letter I've used in the first position or the one I've used in the second, and so on. So what does this mean? What does this look like? This is what we're going to have. Okay. So for the first position, we have 26 letters we can use. But we have already used one letter there. We only have 25 to use. because we cannot repeat. We can only use a letter once. If we have used 25, how many can we choose in that position? Only 24. If we have used 24, that position we can only use 23, and then is 22. So our answer here will be 26 times 25 times 24 times 23 times 22. You can leave your answer in that manner. That's okay. Or if you want, put that in your calculator and see how many ways are there. Are we all together? Very important that we cannot repeat our letters. Okay. Now let's look at the second question. What does the second question mean? So the same, we want to start a password, okay, 5 different letters, okay, so it implies this 1, 2, 3, 4, 5, something of that nature. But now the password must start with the letter D and end with the letter L. So it implies D will be there, L must be there. So what we have to worry about is that position and that position and that position. Are we together? So this is kind of like, so from our 26 letters, the password must start with D and also end with L. Can we repeat in between? No, it's still the same because we can use the letter only once. So from 26 letters, we minus how many? 2 more letters, which is L and D, because our password must start with D or L. And this is what we get. So what it means, now we have 24 letters. Why 24 letters? Because our password starts with D and end with L. So from 26 letters, we can only use 24. So we have 24 there, which is that 24. Because we have 24 for that position now, this position, we have to use 23 because here we have 24 letters. We cannot repeat. We have 23, then follows by 22 letters. And what we do, we just multiply as indicated there. And that's fine. You can leave your answers 24 times 23, multiply by 22. Are we all together? Okay. Fantastic. Okay. Good. Let's look at the next one. Okay. So let's read our question again. 7 cars of different manufacturers. So we have 7 cars. Very important, there are 7 cars of different manufacturers, of which 3 are silver. Okay, what does that mean? If 3 are silver, that implies we have 4, which we don't know, okay? Because we have 7 cars. So 3 are silver are to be parked in a straight line. Are we all together? Now, in how many different ways can all cars be parked? Okay, interesting. So we have 7 cars, but from that 7 cars, 3 cars are silver, and we don't know about the 4, okay? So, but how many ways can we really park those 7 cars together, okay? So, this is counting without repetition, because if I've parked first car in the first position, then for the second parking spot, only 6 remaining cars can park. Then if I've parked the first and the second, then what happens there? Let's look at this. So because we have 7 cars, which is 1, 2, 3, 4, 6, 7. So it's 1, 2, 3, 4, 5, 6, 7 cars. So if I've parked the first car there, okay, which is car number, I take 1 car. So the first car has 7, can choose as the first car where to go. You can go there, or there, or there, or there, or there as the first car. So you have 7 choices as the first car. The first car to arrive has 7 choices. So the first spot has been taken. The next car has how many choices left? If you look at that, the next car has 6 choices, which will be 6. So then the next car, so that spot has been taken, the next car will have what? 5. Then what about the next car? The next car will have 4. Then the next will have 3, then 2, then the last car will have only 1 choice because the rest will be taken. So then to answer our question, we just have to multiply all those choices. And what do we get? We get 7. So we get 7. So it would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And you can put that on your calculator. But this is fine like that, without simplifying the answer. Okay, it's actually better because if you have typed the answer, you put your answer on a calculator and give me a number, and what if your number is wrong? Then we're not sure whether you understand. But if you write your answer like that, if you made an error, you're able to get some of the marks. Okay, you show that you understand that. Are we all together? Now, let's look at the second question. So it's still the same question where we have 7 cars, okay, of different manufacturers. 3 still silver, are we all together, are to be parked on a straight line. Okay, now, if 3 silver cars must be parked next to each other, determine how many different ways the car must be parked. Okay, so now what is this asking is that the silver cars must be parked next to each other. So it implies the silver cars must be, you must have silver, 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 and the rest of the cars. Are we all together? Okay, so I can have silver, silver, and doesn't matter on the sides, or I can have 3 silvers in the beginning and doesn't matter the other 4. So, but the 3 silver must be packed together. So what do we have to do with this question? We're going to apply the fundamental principle of counting, which states that if I have m ways of doing something and n way of doing something, then the total ways of doing that will be m times n. Are we together? So we're going to look at how many ways can we park those silver cars, which there's 3 silver, and other cars which are 4s, and how many ways can we park them? Then multiply that. Then that will give us how many different ways that the car can be parked. So for silver cars, we know this 1, 2, 3 cars. And the rest we have 1, 2, 3, 4 cars because we have 7 cars. Are we together? So to do that, we're going to look at this. So for silver cars, we have 3 times 2 times 1. Are we together? And for other cars, it's 4 times 3 times 2 times 1. And you just multiply that. And that will give us the total ways. Are we all together? Okay, fantastic. Put that in your calculator and you get the answer. Or you can leave it like that. Fantastic. I hope this makes sense. And we'll come back and look at more problems after this break. Welcome back again, guys. So we're still on revision of probability, and we've tried so many problems, okay? And I really encourage you to try even more problems, okay, beyond what are you doing. It's a practice, the nature of how we do mathematics, okay? So let's look at another question, okay? So this is question 6. So the hair color of 30 learners. So now, very important, that's we're doing about the hair color of 30 learners was recorded on the table. So we're talking about 30 learners, okay? So if you look at our table, we can see that the hair color here we have black, brown, and blonde, okay? Can you see that? And we can see from our table we have boys and girls, okay? So we have boys and girls and different hair color, which is black, brown, and blonde. And this table is incomplete, if you can see that. So if you see here, we have 18. So this 18 is 8 plus 4. Is that 18? No. So if I look at this table, that actually 12. So it implies here, there must be like a 6 to give us 18. Can you see that? If I add, I should get 18. And it makes sense because this plus that will also give us 8. So if you get a table like this, which is the contingency table in probability, try complete your table. That's what I'm doing. Then if I look at this, this is 8 plus 4. That will give me 12. And what about here? And this adds up to 30. Okay, we can do it this way. Okay, so if we look at this total, this will give us 10. All together, let's do it. This is 10. Okay, how we could have done that? 4 plus 6 will give us 10. Or we could have went 8 plus 12 is 20. What do we need to get 30? We need 10. So, try and complete your table. Okay, so I've completed my table, even before trying to see what is required here. Now, I've completed my table. I can see I have boys and girls. I've completed boys and girls. They have different hair color, black, brown, and blonde. Okay, so there's something else here I have to complete, so which is 12, because this is 2, 4, 6, 12. What does this mean? We have 30 learners. Can you see from the question given? 30 learners. There are 18 boys. There are 12 girls. Are we together? What does it mean? How many with black hair? 8. How many with brown hair? 12. How many with blonde hair? 10. Are we together? Girls with black hair is 2. Boys with brown hair, 8. Are we together? That's how you read your table. Now let's look at the questions. Calculate the probability that a learner chosen at random will have black hair. What is the chance that if we select a learner from the 30, we'll find that the learner has black hair? Okay, let's look at this. So the table is completed here. So calculate the probability that a learner chosen at random will have a black hair. So if you look at this, what do we have to do? Okay, so there are 8 learners have black hair out of 30. Can you see that? So there's 8 learners with black hair. So this question didn't say a boy or girl. But what do we know? Boys and girls combined, we have 8 learners with black hair. Okay. Then to do this now, what we can say is that probability, very important, probability of black hair, I can use that notation. So it's 8, which is there, out of 30. And I can simplify that. I get 4 out of 15. I can leave my answer as a fraction, or you can write that as a percentage. Are we together? Good. Let's look at our next question. So our next question was, calculate the probability that a learner chosen at random also will be a girl. Can you see it? Will be a girl with brown hair. So will be a girl, okay, will be a girl, but brown hair. Let's look at that. So since a girl is chosen first, okay, so the sample space of 30 learners is reduced to 12 because now we only want to choose a girl. Okay, because there are 12 what? Girls. Okay? Of the 12, only 4 have brown hair because what is the probability that a girl will have brown hair? So we look at girls and the girls is 12. Are we together? So this will give us the probability of blonde hair given a girl is chosen first. That will be 4 out of 12. Are we together? Blonde hair, I mean this one. Are we together? Which is 1 over 3, or you can write that as a percentage. Okay. Our next question, still calculate the probability that a learner is chosen at random. Will be a boy, similar to the other one. Now will be a boy, but with blonde hair. A boy now. How many boys do we have? 18. So what does that mean? Since a boy is chosen first, the sample space of 30 learners is reduced to 18 boy learners. Agreed? And of this 18, only 4 have blonde hair. So let's look at that. Only 4 have blonde hair. And this is we get 4 out of 18. Which is, you can leave it like that, or you can write as a percentage. Then our last question, calculate the probability of a learner chosen will have blonde hair and will be a girl, okay? Blonde hair and will be a girl. So since hair color, blonde, is chosen first, then the sample space is 30 learners, agreed? Is reduced to 10 learners. Of this 10, only 6 are girls. So it implies we'll get a girl is blonde hair, chosen first. We get 6 out of 10, which is 3 out of 5. Fantastic. Okay, guys, so now what we're going to do, we're going to look at another problem, which this one, if I look at this, I can see kind of requires a Venn diagram, and let's see what we get. So you're given 2 events, event C and D. What is given here is the probability of C is 2 times the probability of D. And it's 2 times the intersection of C and D. Remember, this is the same as AND. And this is the same as OR. Are we together? Now, we're also given that the probability of C or D is 0.52. The question is find that. Let's draw a Venn diagram and see what we get. So we have event C and D. What is the intersection? Start with the intersection. Do we know the intersection, the probability of C and D? Do we know that? No. Let's make that Bx. Are we together? Now from there, what we can do, we know that the probability of C or D, okay? So P, and this also means AND, okay? C intersection D, that means AND, and this means OR. Are we together? And that will means AND. So this is the probability of C or D is equals to the probability of C, probability of D, and minus the intersection. Now, let's try substitute. Because we know the probability of P or C, of C or D is 0.52, which is given there. But we know that C, are we together? If we look at probability of C, so we said let the intersection be X. Are we together? This part be X. If that is X, because we know that PC is 3 times X, then we get 3X. And also we know this is X. Are we together? Then what we can do, we can calculate the probability of D. Oh, this is X, not 3X, yes, 3X. So if this is 3X, we can calculate the probability of D. We'll have to divide both sides by 2. We'll get 1.5. And what is the intersection? X. Then from here, what we have to do is to solve for X. And we solve for X. This is what we get. And this is what is required for us to calculate. Fantastic. Okay, we get 0.115. So this is what we looked at. Complementary events, counting principle, tree diagram, independent events, contingency table, and Venn diagram, mutually exclusive and mutually inclusive. Okay? Fantastic, guys, and we hope to see you soon. This is the end of the lesson. I encourage you to keep working hard at home and keep working hard. We definitely hope to see you soon, and bye from us.